No big deal. So last time we were looking at these parametric equations. X equals t squared, y equals t squared minus 3t, and t can be any real number. And we plotted a few points. I let t range from -2 to 2 just to kind of find some nice values. The x values were, let's see, 4, 1, 0, 1, 4, and the corresponding y values were, let's see, -8 plus 6 is -2, and then -1 plus 3 is 2, and 0, and then 1 minus 3, and then 8 minus 6. So these are the points we're going to plot. Now, it's kind of worth doing these in kind of order of increasing t values to think about what direction your particle would be moving if you were thinking of it that way. I'll try to make this graph look pretty decent here. So let's see, 1, 2, 3, 4. Do be careful if you're graphing parametric equations. It's really easy to start accidentally grabbing t values instead of x and y values. So then I'm graphing this and saying, okay, x is 4 and y is -2. And then x is 1 and y is +2. So we're way over here. And then x is 0, y is 0, and then x is 1. Sorry, x is 1, y is -2. Right, see, even I'm doing it. And then x is 4, y is 2. So we're going this way though, right? Here's time equals -2, time equals -1, time equals 0, time equals 1, time equals 2. So we're doing this like something that looks kind of like this. I'll try my best to draw it here. Oh, so I don't really love that arrow that I just drew because that's kind of the opposite direction that time is flowing. So you really shouldn't draw the ends with arrows. You should draw the arrows going in the direction of time moving forward. And same goes down this way. Like that. Cool. And you could certainly find this point of intersection on the x-axis just like you usually would by finding, well, usually to find the x-intercepts, we set y equal to 0. So that would be setting t cubed minus 3t equal to 0. Factor out a t. So you either get t equal to 0 or t equal to plus or minus √3. And when t equals plus or minus √3, x is going to be t squared, which is just 3, which is how I knew that that was the point right there. Okay, so then we should talk about all the other stuff. Derivatives, concavity, that kind of jazz. So how do we find the derivative? And I know we did this in class last time, so we're kind of repeating some of it. It's fine. So the question I wanted to ask really is, this is part A. Sorry. Where do we? What's that? Oh, sorry. Yeah. So where do we have horizontal tangent lines? Well, if we look back at the graph, it seems reasonable that they might be. And again, my graphing is never perfect. So it might be somewhere about right here. Like it looks like t equals 1 and t equals -1 are potential places where we could have a horizontal tangent line. In a similar way, it looks like t equal to 0 is a place where we might have a vertical tangent line. Well, let's actually take a look and see. So, and this is where I want to kind of do just a little bit more. How do we find where dy dx is equal to 0? Or specifically, how do we calculate dy dx? Well, it's kind of funny because it looks like you're just doing the division that would work. Meaning, we are going to calculate dy dx parametrically, dy dx, as dy dt over dx dt. And it kind of just looks like the division, right? Where the dt's cancel. And it's not 100% wrong to think of it that way. But here's what's really happening. It's really coming from the chain rule. So if we look at this, we look at y as a function of x as a function of t. And you don't need to know. I mean, do you need to know this? But if you take the derivative of this, using the chain rule, we get y prime of x of t times x prime of t. But if we write this in kind of the more usual Leibniz notation, this is the derivative of the function y with respect to the variable t. This is the derivative of the function y with respect to the variable x. And this is the derivative of x with respect to t. But then if we want to isolate this, divide both sides by dx dt, and you get exactly dy dt over dx dt equal to dy dx. Totally works. So I don't do this every time I'm thinking about taking the derivative, but I do think about it sometimes. Like, oh yeah, it's really for the chain rule. I usually am just remembering that I can think of the dt's canceling out here, but it's nice to kind of have the bigger picture. So if I want to find where dy dx is equal to 0, well, I need what y and x are. So again, x is t squared, y is t cubed minus 3t. And be careful, don't make the mistake that I used to make where put the x thing on top and the y thing on the bottom because the x thing comes first. The y thing goes on top, just like with slope, right? Y goes on top, x goes on bottom. So here, my dy dt is 3t squared minus 3. My dx dt is 2t. And so my dy dx is going to be 3t squared minus 3 over 2t. And if I set this equal to 0, I'm really just going to set the top equal to 0. Now, I should be a little more specific here. You get a horizontal tangent specifically when this is equal to 0 and the bottom is not equal to 0, right? You can't have 0 over 0. That's a totally different animal. You might still get a horizontal tangent there, but you have to do a lot more like with L'Hopital's rule. So here we would just set 3t squared minus 3 equal to 0, and we're going to get t squared equal to 1. T is equal to plus or minus 1. Not surprising, right? That's kind of what we thought it was going to be when we looked at the graph. So depending on how the question's phrased, we should probably answer the question in terms of x and y. So we're going to have a horizontal tangent at both x equals 1 and y equals negative 2, and x equals negative 1 and y equal to positive 2. Sorry, I mean, so again, I made the mistake of thinking of t as my x coordinate instead of x as my x coordinate. That's t equal to 1, x is 1 squared, which is 1. That's t equal to negative 1, x is negative 1 squared, which should be positive 1. Which is obvious if you look back at the graph. I was just looking at my graph, I'm like, that doesn't seem right, that I'm getting x equal to 1 and y equal to 2 and x equal to negative 1. That was totally wrong thing. The graphs are good. What about a vertical tangent? Well, vertical lines have undefined slopes. So we're really looking for where we have an undefined slope, specifically where denominator is 0. And again, you don't want a 0 over 0 situation. So you want specifically the denominator to be 0 and the top not to be. So that's just going to be where the denominator 2t is equal to 0, which is just going to give us t equal to 0, which is not surprising having looked at the graph. So then we want to ask about, now I will say, generally, I wouldn't say we usually talk about talking about derivatives of parametric equations. That's not true. We totally comes up in 21D. Talking about concavity parametric equations, less so. But we're going to now because it helps us talk about the second derivative. So, and again, I'm going to refer back to this. It certainly looks here that from t negative all the way to t equals 0, that looks like it's concave down to me. And then from t0 onward to t being positive, that's looking like it's concave up to me. So that's my guess for what's going to happen. Hopefully our work will bear that out. Let's write down the things again. I've always, not always, I've tried to do, to label things appropriately. I always fail about 20 minutes in, so we'll see. So concavity. So let's remind ourselves that we have x is equal to t squared, y was equal to, what was y equal to? T cubed minus 3t. And then we found that dy dx is equal to 3t squared minus 3 over 2t. So we have to be a little bit careful when you're finding the second derivative. Yeah, here's the way I kind of think of it. So I'm finding the second derivative of y with respect to x. So that's going to be the derivative with respect to x of the first derivative with respect to x. Okay. Interesting. I would never thought of it that way. That's fine. So what I'm really kind of thinking of is this is just another, this is kind of like my new y. This is my new y. It's really a function of x and a function of t. So the same kind of thing that we did before works, meaning I know that dy dx is equal to dy dt or dx dt. And all right, this is dy prime dx is exactly going to be dy prime dt over dx dt. Or if you prefer, the derivative with respect to t of the derivative of y with respect to x over dx dt. It's kind of funky. It's not maybe exactly what I would have expected as a student the first time around, but it's exactly what we get. You can do more of a chain rule kind of thing again, but it's really the same idea as what we did before. So when I'm thinking about taking the second derivative, I'm like, oh, I take the derivative of my first derivative with respect to t, but then also divide by dx dt. To that end, it's going to be a little bit easier to not do the quotient rule here. I would much rather rewrite this as 3t squared over 2t minus 3 over 2t, or 3 halves t minus 3 halves times 1 over t. It's a little bit easier to differentiate. So then actually finding the derivative here, we're going to get, so the derivative of this is going to be, let's see, the derivative of 3 halves t is just 3 halves. And the derivative of t to the negative first is negative t to the negative second. Divided by the derivative of, well, dx dt is still 2t like it was before. So we've got that. I would probably simplify this. So I'm going to write this as 3 halves times 1 minus and minus is plus 1 over t squared, all divided by 2t. Notably, this is never equal to 0. So what does it mean that the second derivative is never 0? You're close to what I'm getting at, but that's not quite true, because this one certainly can change concavity because we can end up dividing by 0, or really it changes signs when t goes from negative to positive. But you're right, there's never going to be a place where it's equal to 0, which means there's never going to be a point where we have an inflection, because that's where we would typically find our inflection points, where the concavity changes, where the second derivative is equal to 0. Well, let's take a look here. So if I simplify this a little bit, do I really want to simplify this a little bit? I really don't. I'm just going to talk about how this is certainly positive if t is positive. Right? The top is always positive. The bottom is 2 times t, which is positive. T is positive. And similarly, this is going to be negative if t is negative. Which again, certainly goes with what we were saying. So what we're really saying here is this is concave up if t is greater than 0. And it's going to be concave down if t is less than 0. I think there was one other thing I wanted to say there. No, I guess not. So yeah, it's kind of weird, but like, right, we wouldn't call, I mean, really, I should say, we only really talk about inflection points in the context of actual functions. And this isn't really a function, so it doesn't really make sense to talk about the inflection point. Because usually inflection point is kind of like a left to right kind of idea. Just like a relative extreme is a left to right kind of idea. Yeah, inflection points are weird the way there's very like specific things we say about inflection points, and yeah, they're kind of strange. What else to say here? So dark. Ooh, yeah, all right. So let's look at some other examples here. Yeah. Sure. One second. I feel like I need to turn on some lights. It's just it's too dark for me. If they get any more, it's too dark. Unless you say, oh man, that's all right. I can do a little bit of this. I'll survive.
It's not that bad.
It's pretty bright. I feel like I look like it's hard to see to me. I can handle the darkness. So let's see, where are we going next? More parametric. So what else? I should say, what else do we have about parametric equations that it might be confusing? Do we talk about integration with parametric equations?
I did.
Yeah, okay.
Areas of surface of revolution for parametric.
Oh, that's right. And also the arc length stuff too, right?
Yeah.
Yeah, surface area and also typically sometimes arc length anyway. So yes, let's see here. I definitely have some examples. Sorry, my notes are kind of all over the place here. One moment. I don't want that. I don't want that. Yeah, let's look at this. No, not that. That example is terrible. Let's just tear everything. Yes. Sure. Okay, you're garbage. That's kind of fun then.
Yeah, we did arc length.
Okay, sure. Let's look at the following examples. So how do we find arc length? And we'll also do surface area. Say the following parametric equations: x equals to t over 1 plus t, and y equal to the natural log of 1 plus t on the interval from t equals 0 to 2. So this is where we're finally getting back to when I said way back when we were talking about arc length, how there's a third arc length formula. So here are your 3 arc length formulas. It's either the integral from x equals a to x equals b of the square root of 1 plus dy dx squared dx, or it's the integral from y equals some c to y equals some d of the square root of 1 plus dx dy squared dy, or finally, parametrically, it's the integral from t equals something to t equals something, say alpha and beta, of the square root of dx dt squared plus dy dt squared dt. All these integrands, the square root of whatever times d whatever, these are all different versions of what we call ds. I'll say this: if anyone's ever asking you to calculate arc length or surface area, you can generally, unless they've done a bad job writing the problem, expect it to work out relatively nicely. That is what I would encourage you to think of. These integrals shouldn't suck. If they do, it was either an accident, someone made a mistake. You might have been a student reading 2 different parts of one problem that I was helping someone with the other day. I got an email like, how do I do this problem? And the problem was that we'd used X from problem 29 in the textbook and Y from problem 30 in the textbook. That's stuff that's not going to work. So make sure you read the problem carefully. For this one, let's find the stuff. So I'm going to I would probably do some work off to the side. Dx dt is going to be quotient rule, fine. Bottom, to the top, minus top, to the bottom, all the bottom squared. Okay, that's going to be all right. That's going to be just 1 over 1 plus t squared. And then dy dt is just going to be 1 over 1 plus t.
I have a question.
Yes.
In my notes, like it's the same thing, but it's like instead of dx dt, it's f of t, and then it's g of t for dy of t.
Sure, because they're probably saying that your parameterization is x equal to f of t and y equal to g of t.
Yeah, and then
yeah, totally the same.
Like how f prime of c is equal to g prime of c, which is equal to 0, then f prime of t cannot be equal to 0. Do you know what that means?
Not exactly.
Okay.
Not off the top of my head. Like,
Yeah.
so they're saying f prime of c?
Of c. Like
what's c? Okay.
Equal to g prime of c, then that's equal to 0, but f prime of t cannot be equal to 0 when t is not equal to c. I don't know, I can ask.
We can look at it later. Yeah, that seems weird. So then anyway, throwing this into my into my integral here, I'm gonna have the integral from t equals 0 to t equals 2 of the square root of this squared. So 1 over 1 plus t to the fourth. And now I'm going to be smart about this. I know I'm going to get 1 over 1 plus t squared, right? Because I'm squaring this derivative, but I'm going to want a common denominator. So what I should really just do is say that this here is equal to 1 plus t over 1 plus t squared. I multiply the top and bottom by 1 plus t. And then when I square that, I'm going to get 1 plus t squared over 1 plus t to the fourth.
How come it's from 0 to t instead of 0 to?
Because I made a mistake.
Oh,
Cool. So then, interesting. So now we have to be, I don't know, smart, maybe. So this is looking to me, so I'm worried. I know I have an answer somewhere over here, but if I multiply this out on top, I've got t squared plus 2t plus 1 plus 1 is 2 over 1 plus t to the fourth. This seems worrying. Don't like it. Definitely not. So I know it's not partial fractions, at least not yet, because to be partial fractions, you can't have any roots. It's just rational functions over rational functions. I'm going to cheat and look at the answer because I know it's available. Because I feel like it's like IBC. Okay, when you're doing problems, it's okay to look for outside help, right? You don't have to struggle with this forever and be like, I don't know what I'm doing. It's definitely part of the learning process. Find an answer and then figure out how to work through it. So, that did not actually be there. Where are you? Cool. Let's take a look. I wouldn't be surprised if it's not here. It's disappointing, but fine. 1415. Answers given. If you get stuck, come see me. All right. So the answers are here, or the answer is here, but it's just like an answer, not a number. I'm really curious. It feels like it could be that. All right. So let's look at what we see. And maybe sometimes we give up. That's all right. So if I'm looking at this, yeah, I'm integral from 0 to 2, and it is a length of the square root of 1 over 1 plus t to the fourth. And I'm going to go back and actually undo what I did. 1 over 1 plus t squared. I don't love it. I feel like there's something I'm missing here. Okay, let's try this. Let's factor out. Gosh, I keep wanting to write t. Let's factor out a 1 over 1 plus t squared. And then we're left with a 1 over 1 plus t squared plus 1. Oh, I think I'm seeing where this is going to go. So then the square root of 1 over 1 plus t, whoops, you might want to see what I'm writing. The square root of 1 over 1 plus t squared, that can be this 1 over 1 plus t. So we have the integral from 0 to 2 of 1 over 1 plus t times the square root of 1 over 1 plus t squared plus 1. I still don't love it. I feel like you might be able to do a u substitution here. Now these I'll be honest, these square root ones often trip me up. Like I have a hard time figuring out what I'm supposed to do a lot of the time with these. Yeah. I don't even have any suggestions.
Well, if you did a u sub have 1 plus t, then the u would just be 1, right?
Right.
So then when you go to.
Oh yeah, I think yeah. So the problem was I was dismissing it because it didn't feel like it was going to do that much for me.
Yeah.
But I think it might. So du is dt, and then we're going to rewrite this as the integral. Let's also change the limits of integration because why not? From 1 to 3 of 1 over u square root of 1 over u squared plus 1. And now I see something. I can rewrite this as the integral from 1 to 3 of 1 over u times the square root of 1 plus u squared over u squared. Oh yeah, I'm not real thrilled about this, but here's what we've got. Let's make that square root of u squared just a u not inside the square root. So I'm going to have the integral from 1 to 3, the square root of 1 plus u squared on top. And combining all the things I have, what do I have on the bottom? Well, I've got a u times another u, which is a u squared. Okay, prepare for disappointment. Well, not this, I mean, I'm thrilled about what we're about to do. What do you think I have to do now? What kind of method could we use here? Not a u sub. It's a trig substitution. Fun time. So we're gonna let u equal tangent theta. Why tangent? Because 1 plus tangent squared is secant squared. Right? I know it was tangent from the get-go because I had a plus in my square root. And plus looks like t, and tangent starts with t. So u equals tangent. Du is secant squared theta d theta. Oh my god, this is gonna be this. I probably wouldn't change the limit of integration here because I don't want to write arctangent of 3. That seems dumb. So I'm just write the integral of the square root of 1 plus tangent squared over tangent squared times secant squared. Yeah. So maybe, I mean, fine. We might as well finish it off here. We've done this much. So that's going to be the integral of, well, the square root of tangent squared is secant squared, or sorry, 1 plus tangent squared squared is just secant. So we're going to get secant cubed theta over tangent squared theta. Now what? Good question. So here's what I found. I was thinking about this the other day. When you have just powers of trig functions, like secant to a power, tangent to a power, sine to a power, but like I think you can always make it work eventually. Sometimes it's super duper gross, but you're never really stuck. So my suggestion here would be one of two things. You can try a u sub. I feel like letting u equal tangent will probably work. I think. Maybe not. No. So u equals tangent is no good. U equals secant might work.
I think secant would work.
Yeah. Except for no, I don't. Oh no, this is the terrible situation. This is so as I mentioned before, when you have an odd power of secant and an even power of tangent, that's when you have to do like the integral of secant cubed or secant times tangent squared. That's when you have to do integration by parts and a trig sub and end up getting the integral back that you started with and then add it over to the other side. So this is probably terrible. So what we should do instead, if that seems terrible, I'm going to write it in terms of sine. That seems like a better option. So, gosh, I didn't realize the problem was going to be so long. That's picking an easy one. So let's see. So we're going to get the integral of 1 over cosine cubed over sine squared over cosine squared, which is going to equal the integral of 1 over cosine cubed times cosine squared over cosine. Sorry, over sine squared. Sorry, I was doing, and then we're going to end up getting the integral of 1 over cosine theta times 1 over sine squared theta. Terrible too. Good God. What a terrible, awful problem. Yeah. I don't know. I know it's doable. I just don't want to do it. Here's what, oh God. Well, what I was, well, right. So what I was going to do, is this. Oh my God, this problem is, I'm going to multiply by a code. I'm going to put one of those cosines back. And now I can let u equal sine. So if we let, I shouldn't use u though, because I've already used u. So let's use a different letter. Sorry. Let's use, we've already used t as well. Let's use w. Sure. W is sine theta. dw is cosine theta. D theta. And then this is going to equal the integral of, so there's my dw. And then sine squared is u squared, and cosine squared is 1 minus sine squared, which is 1 minus u squared. And now we can use partial fractions. Okay, I think I officially quit. This problem's stupid. Yeah, we can. Yeah, partial fractions. I will tell you because I have the answer in front of me, just in case you want to actually be a masochist later. The answer is the square root of 10 over 3 plus the natural log of 3 plus the square root of 10 plus root 2 minus the natural log of 1 plus root 2.
The 1 over u squared times.
Well, it's actually 1 over w squared times 1. Because I don't know how else to do it.
But what if you just multiplied it out and then it wouldn't work?
And then what?
And then it would be w squared.
Minus w to the 4th.
So then can't you just integrate that or no?
No, if it was 1 over w squared minus 1 over w to the 4th, sure, but the whole denominator being more complicated means we're typically having partial fractions. So what you would do is you would say my 1 over w squared times 1 minus w times 1 plus w, right? That's how you factor it. You'd say that's a over w plus b over w squared plus c over 1 minus w plus d over 1 plus w. And, yeah. Trig sub, so you might be able to do trig sub here, although I don't, but so here's the thing. Trig sub would just be undoing the u sub we just did. Right, if I let w equal sine theta, I'm back to where I literally am undoing the work I just did. Oh, wait, one more thing. Also, typically, although not like 99% of the time, you're only doing a trig sub if you have a radical. There's like one example where you do a trig sub where you don't have a radical, but other than that, every trig sub has a square root of 1 minus x squared or x squared minus 9. Yeah.
Where did the w come from under the a? Because you have like w squared.
Right. So that's the thing. When you have a partial fraction decomposition, you have to have, whenever you have a repeated linear factor, you have to have that highest power and every lesser power.
Oh, okay.
So like if I had a 1 plus w cubed, I'd have a d over 1 plus w cubed plus a e over 1 plus w squared plus an f over 1 plus w. Okay, I'm officially done with this problem. Let's gotta try something else. I don't know. I feel like I'm forgetting about something about this. Oh, arc length. Or no, surface area. I'm terrified. This is the problem when you just say like, yeah, I can do any problem on this thing. Sure. Sometimes they get really hard. Let's take a look here. What time is it? All right. So all right, I thought I had more examples. Oh, you know what? I do, but on the other side of this page. Cool. So let's look at this example, which I think is not going to suck, but who knows? So let's find the surface area of the following parametric equations. X equal to, oh, this is going to be too easy. Fine. It's fine to do an easy one. Nothing wrong with easy problems. X equal to 2 plus cosine t, y equal to 1 plus sine of t, where t goes from 0 to 2 pi. And we want that to be revolved around the x-axis. Okay, so as is usual, right, surface area is the integral of 2 pi r ds. And I don't know what my curve actually looks like. I'm just going to make it up. Pretend it looks something like, I don't know, x is going from 2 to, yeah, sure, whatever. Something weird like that. Let's pretend that's my curve. And I'm taking some little sliver of it and going around the x-axis. I'm taking this little thing and there's my little band. Like that. The surface area of that rubber band is 2 pi r, right? The circumference of that circle. That circle multiplied by the width of this strip, which is ds. Okay, so what's my radius? Y. Definitely y. So here it's going to be the integral from 0 to 2 pi of 2 pi times y times my ds, which is the square root of dx dt squared. So dx dt is negative sine t squared plus dy dt, which is cosine t squared dt. So there's my radius, which is equal to y. There's my ds. But the square root of sine squared plus cosine squared is just 1. So this one is way less stupid than the last one. We're going to get 2 pi times the integral from 0 to 2 pi of just 1 plus sine of t. And that's actually a very reasonable thing to compute. It's going to be 2 pi times the integral of 1 is t. The integral of sine t is negative cosine of t from 0 to 2 pi. So we end up with 2 pi times 2 pi minus 1, right? Because cosine of 2 pi is 1 minus 0 minus 1. Now let's say if the 1's cancel, I think we just get 4 pi squared. And then just because it seems worth asking, if instead we were going to go around the y-axis, our surface area would be the same, except to be 2 pi times the integral from 0 to 2 pi of our x, which is 2 plus cosine t. Same ds. Kind of neat. And that one would be just as easy to calculate. I don't think that'd be around the y-axis. You could even probably let's think before you speak here. Yeah, you could totally go around even a different axis, which I know is not something you usually do for surface area, but like we could go around the axis, like for example, y equal to -1, and our radius would be y minus minus 1, which would then just be 1 plus sine t plus 1, so 2 plus sine t. Kind of cool. Usually, I rarely see people ask surface area questions around lines other than the x and y axis. Right? Volume for sure. People will ask volume questions some of the time around different axes. The surface area is atypical to say the least.
General, whenever it's y-axis, the radius is x.
Correct. Right, because what you're doing here, right, you're just imagining this little bit here, and you're saying, okay, well, if I'm going around the y-axis, I'm just saying the radius is how far I am from the y-axis, which is x. Similarly, if I'm going around the x-axis, the radius is just how far I am from the x-axis, which is y. Yeah, it's always like that. What else? And we were going to talk about vault area as well. Area is weird parametrically. Yeah. Let's see here. Do I have? No. Let me think here. I don't want to give you something terrible. Oh yeah, interval. Okay, cool. So this is where I think things are super funky. So let's say let's say I have the parametric equation x of t equal to 4t cubed plus 3t, and y of t equal to t squared plus 1, and t is between 0 and 1.
So is the only difference between like surface area and our plane for parametric side, whatever I'm picking, compared to normal is that there's an x equation and a y equation? Is that what's different?
Yeah,
Okay.
yeah. And typically, if you're doing surface area with if your function's written in terms of x, you're just doing the square root of 1 plus dy dx squared times 2 pi times your radius. Now, if you're going around the x-axis, your radius is y. That means you have to choose the function, what y is equal to. Or if you're going around the y-axis, your radius is just x, and you leave x alone. So it's the same idea, just a little different.
Okay.
So here's our parametric curve, and we want to be, so we're going to say that let R be the region bounded by the curve that we just talked about, the coordinate axes, and x equal to 7, which is what you get when you plug in t equal to 1. So just to give a rough sketch of the graph, when t equals 0, x equals 0, y equals 1. When t equals 1, y equals 2, and x equals 7. So like somewhere over here. So we're probably doing something like this. And we're looking for this area. Keep doing this. So typically, if I were to write this as y equal to a function of x, then I would say that my area is equal to the integral from x equals 0 to x equals 7 of f of x dx. I don't remember how this works. I'm pretty sure I know how this works. It's just super funky. So then, oh my gosh.
We didn't even do this, so I thought
Sure.
we just did surface area.
Yeah. Oh my God, brain. But you can do this kind of, again, it's kind of this just, I feel like a lot of this stuff is like, you're doing tricks. So, yeah. So if we say that x is equal to g of t, y is equal to f of t,
Would you just have to convert it to a Cartesian equation?
but sometimes it's not possible. Like it might work out here, it might not, but it might be possible to be terrible. But the thing is, we can totally do this thing where we say, well, I'm going, let me be smart. Let me just make sure I'm not telling you guys the wrong stuff before I do something silly here. Let me just look, yeah. Yep, okay, cool. Yeah, of course. Yeah. So literally, what we're going to plug in for y is what y is equal to, and x is, well, dx dt is equal to g prime of t. So dx is equal to g prime of t dt. So y is what y is going to be, t squared plus 1. And dx, if we take the derivative there, you're going to get 12t squared plus 3 dt. I feel like, so I've seen this in the textbook before where they do this kind of thing. I feel like that's not, in my opinion, super helpful. To be perfectly honest, I think it's easier to look at this and be like, yeah, put in what y is. So if you're integrating y dx, which is what we typically do, we're going this way. And we're adding up these rectangles. Put in y equal to the y function, and dx is literally just your derivative times dt. The one thing to be careful about, which I've seen people ask about and other stuff, is sometimes like basically this gets kind of reversed if you're measuring your area down to like the y-axis instead. Does that make sense? Like if instead I was trying to describe like this region here instead, then I'd be trying to integrate, like with respect to y instead of with respect to x probably. So I'd probably do something like, in fact, we'll do it in a minute here, just to kind of see. But to finish this problem off here, not particularly nice. We're gonna have the integral from 0 to 1 of t squared plus 1 times 12t squared plus 3, which is going to be 12t to the 4th u plus 3t squared plus 12t squared is plus 15t squared plus 3. Which, okay, not particularly nice. But yeah, if you wanted this little area over here, the way you would do it would be the same way, except you're kind of thinking about horizontal things here. So then you'd be doing the integral of x dy instead of y dx. So this area here would be the integral of y dx. Still with the same t values. So that would be the integral of t squared plus, oh, that's I'm saying the same integral and I don't mean to be. Not y dx, my God. Sorry, deviant, right? How did I let myself do that? We know that this horizontal strip has a d what? A dy, right? Small change in y. Sorry about that. Killing myself over here. So really this should, that area there would be the integral of x dy, right? X is a function of y giving us the length of the thing, and then the dy giving us that. So that would end up being the integral of 4t cubed plus 3t times 2t dt. I remember this being an issue, I think last quarter maybe, where there was some weird problem like this where like you had to do it the other way because of how things were oriented. I would say this particular formula is not super important. Usually we don't get asked a lot about finding area parametrically, but you could be.
Well, I have them where you did the second part when you did horizontal strips, can't you still do a vertical strip?
So you could do vertical maybe, except
Your top one would just be whatever
your top line should be like y equals 2.
Yeah.
So I think you could, but I feel like it'd be tricky because I don't know. Because if I want to do it vertically, I'm thinking about that vertically. I've got this vertical strip. I don't know how I would probably have to parameterize this. So I guess if this is going from the point 0, 2 to the point 7, 2, because that's what the other point was, I could say, well, I know what, here x is whatever, x of t is 4t cubed plus 3t, and y of t is t squared plus 1. And then I guess I could say, well, this is going to be y of t is equal to 2, and x of t is equal to 7t, where t goes from 0 to 1. But I think you'd have to do some sort of weird parameterization so that then you can do the subtraction. I feel like it'd be dicey.
Yeah, okay.
So yeah, parametric equations, I feel like what you really need to know, what I think you need to know, is how to differentiate them, maybe how to find the second derivative, how to find arc length, how to find surface area. And need is probably a strong word there, but what you might be expected to know for your final exam.